Hi, I'm Caesar. In this video, or maybe in this series, I would like to talk deeper about the computational fluid dynamics method. And if you are expecting we will discuss about the software, maybe it is not right for you because our focus will be on the theoretical side. So we will discuss about how the computational fluid dynamics works, like the mathematical background, or maybe the discretization, the computation, like the coding maybe. So after you finish this series, you can understand how they works and how to apply it in your daily computational fluid dynamics works, like how to make the best setting and how to troubleshoot if there's any error if you are running the simulation. Or maybe if you want to make your own computational fluid dynamics software or solver, because sometimes if we buy the commercial software, sometimes it's just too costly for your so simple problem. And maybe sometimes we cannot also understand the detail of the code. So if we want to make some specific research, let's say, we don't really know how the background of the software. So sometimes the best way to solve or to do your research is by using your own CFD code. And I hope this series will be a long series with comprehensive, detailed, like the theory. And maybe for demonstration, sometimes I will also use MATLAB just for a small demonstration about the algorithm. Or maybe I also will use the OpenFOAM software, which is the free and open source. You can download and install it without any price, and you can also access the code of the OpenFOAM and you can edit it. But of course, it will be has some certain certain policy from the license itself. So let's just get started to this first part. The computational fluid dynamics, or CFD, commonly use the finite volume method, or FVM. Maybe you ever heard about the finite element method, which is commonly used for the structural analysis. And to begin discuss about the finite volume method or the computational fluid dynamics, we will discuss first about the finite difference discretization. This is actually just very, very basic of the idea how the numerical simulation or numerical method works. So, as you know, computational fluid dynamics just works like the basic physics itself. We know we have the the mass conservation and energy conservation, and also the momentum conservation. Let's say we have the Newton's law to calculate the motion of a rigid body. Let's say we have like a particle with specified x and y position in specified time. We can easily use the Newton formulation, F is equal to m times a, to get the velocity and acceleration, or maybe the position each time, with really easy analytical solution. So we get the exact solution. But unfortunately for fluids, we don't have that such simple equation. So the the fluid consists of like pressure and velocity in x, y, and z direction, and it will be varies in every specified points. And we have fields. If you know the fields, like everywhere we have some specific value of pressure and velocity. And sometimes we get also the turbulence, some random motion or some swirling motion everywhere, so solving this Navier-Stokes equation is literally impossible for your daily working. Of course, you can solve the Navier-Stokes equation if you make it or simplify it by using like one-dimensional or maybe incompressible flow, or maybe we just ignore the viscosity or we ignore the turbulence. But unfortunately, that not will be the case in the real-world engineering application. For example, if you want to calculate the drag force in an aircraft, of course you can do like one-dimensional, or maybe you can do two-dimensional for airfoil, let's say. But it's the simplification is just not the case for daily engineering application. So instead of solving the equation, maybe we hope mathematician will solve the analytical description, or get the better solution for the Navier-Stokes. But I don't think we will wait that now. So the best way to use by engineer is to solve it using the numerical method. And the numerical method is actually just changing or maybe convert from the partial differential equation into the algebraic equation or discretized equation, like the plus, minus, and division and anything like that. So we can solve it easily by computer, let's say. There are some ways to convert the equation from the differential equation into the discretized form, like the integral method and some series expansion and anything. But maybe the most popular used is using the Taylor expansion or Taylor series. So we can expand it like this. Just move the differential equation to the left side of the equation, and we get this equation. Of course, we also get some factors like this one. If we continue the series, we will get like n equal to 2, 3, 4, 5, and etc. But as the number of n goes by, keep getting higher, this right factor will be diminished. So sometimes we just ignore this and say it is just like the truncation error. So actually the discretization is not solving the whole equation itself, it just literally the approximation. So we just can ignore this. This factor will be minimized if we get the number of delta x, or the like the discrete value of the space and time getting smaller, let's say. If we not choose the small enough delta x, the truncation error will be high. But this is not the case for the typical calculation. So the error is just like 1 or 0.00 something percent. So we can just ignore this truncation error in the typical case. So if we see this equation, you see that the u I plus 1 is equal to u in the x plus delta x. If you remember, if you can imagine it like this, the function of x plus h, or the delta x, minus the function of x in the x position divided by the h, or this one is like the delta x. So if we make this h very small, limit to near the zero number, this equation will be the differential equation itself. So it will be like the exact solution. It just gives you the idea that actually this is exactly the same or approximately the same as the differential equation with some truncation error. Okay, let's us discuss or maybe visualize it in the graphical way. Let's say we want to calculate the slope of this red curve in this xi. So by using our previous equation obtained for this Taylor series, we get this approximation with the blue dotted line. So if we want to calculate the slope here, so we just use the ui plus 1, which is here, ui plus 1, this point, minus ui here, minus this, and divided by delta x here. So now we just ignore the j, we will explain it later. So you get the value or the approximate value of this gradient. So if we expect have a better gradient in this point xi, we can just make the delta x even smaller. But in numerical analysis, if we get the delta x just too small, sometimes the number of division will be too large, and sometimes it will make your computational effort and time even larger, and sometimes it will cost more. So this is the forward difference. So forward difference is just means that we calculate the point at I with the next value, which is I plus 1 or x plus delta x. So we also have another option, let's say the backward difference. So we can calculate this slope by using the value of u at I minus by the u at previous I or I minus 1, like this. And sometimes if we use the wrong discretization method or the different equation, sometimes the slope is not well suited to the curve itself. For example, this curve, the blue curve, is not, this is very far from the slope we want to calculate, which is the black one. It doesn't mean that the backward is, like the forward is better, but it is just like the illustration that the different choice of the equation will lead to different results. For example, if we want to calculate here the slope, this point, of course the forward difference will be like worse than the backward. So it is like, that's why you must understand its equation used in the computation. Sometimes it leads to like not only bad quality result, sometimes it is also affect your stability and convergence. We will discuss it in the maybe in the other part. And the third idea is the central difference, which is using the previous location I minus 1 and the next location, which I plus 1. If you take closer into this equation, you don't have the ui here. So you just calculate the new value of ui from the neighbors. So you will have theoretically smaller error. So smaller error here, just read in the delta x square. So if we previously just the truncation error is with the order of delta x, this one has a larger or like higher order of the delta x, which means it will be more like smaller truncation error. But we don't really need to discuss it further, but because it is just like the consequence of the equation. And sometimes the central difference will be the best choice in some cases, but you must have two options here. Sometimes you just to initiate everything, maybe we will discuss it in the later part. So you just need to understand the difference between the forward, backward, and also the central. Sometimes it is also mixed. For example, if you want to use the backward difference but you put one half here and new point here, you just make 2 points. So sometimes it is also like different, like other different idea. You can do whatever you want as long as it is stable on anything. There's a lot of list of these equations, but you must understand these 3 basics equations. And next we want to talk about the 2-dimensional. If we previously just discussed about the 1-dimensional, like the UI, let's say the u in the x direction in only depend on one coordinate, one spatial coordinate. Now if we want to make it dependent into coordinates, we just use the j. For example, here the value of u here is uij, so I is for the I think I should exchange this, the I here and the j here, it is actually just the same, and it just works the same, something like this. So I think I need to change it. Okay, I've changed it. So the I represents the x direction. So if the I plus 1 means that it is the location is the x plus delta x here. So if you want to use the forward difference, we can visualize it like this for the 2-dimensional. And let's say you want to calculate the du divided by dy, so the points will be here, like the equation will be like ui comma j plus 1 because it is in the y direction, minus I comma j. So I hope you get the idea. So it is just the matter of the this point. Or sometimes you can also replace it by time. For example, I comma g, so the g is the time if you want to simulate the transient equation, let's say. So the next du per dt, for example, is ui comma j plus 1, let's say. We will maybe make some example in the next part. So this is the forward difference, and the backward difference is just the same, the location is just reversed. So the uij minus ui minus 1, so it is minus 1 in the x direction. If we change to du per dy, it will be like uij minus ui comma j minus 1, so it will be underneath the ij. And also the central difference, we use 2 neighbors data to calculate or to complete this equation to get the new value of the uij. And these are the equations. You can screenshot it, or you can refer to the books from the Anderson. Actually, it like there are 2 books of computational fluid dynamics, and the name is the same, the Anderson, but I prefer to use this Anderson, but it is more detailed compared to the other Anderson. If you want to get like easy to learn, maybe the other Anderson is better, but it's up to you. It's actually just the same, the equation, just different pace of the discussion. And the next question is, what about the next order of the differential equation? Let's say the d squared 2 divided by dx2. We actually just utilizing the same Taylor series, and like move the squared u divided by dx squared to the right part or the left part of the equation instead of the du per dx, rearrange it, we get this equation. And we can also rearrange it like the other possibilities, something like this. So sometimes it is depends on your code. Let's say if you are coding in your MATLAB or something, sometimes it's just more convenient to use the other form compared to the other. So it is just a matter of practicality. And sometimes the index itself is not always to be like this. Let's say if you want to change the equation like I plus 2, you can do that, but this I should be like I plus 1 and this one should be I. So the index is just moving, depends on your own case or your own code. Let's say if you want to make the index in the MATLAB, I start from 2, let's say, you just like I plus 3 or something like that, as long as it is always consistent. I think that's all. If you wonder how to solve it, like we have a bunch of equations in the, the number of I will be like 100 or j will be like 100. So sometimes it is become really hard to solve by hand. So sometimes we just move it, or we just transform it into matrix form, and that matrix will be solved by various scheme, let's say with the implicit, explicit, or upwind and anything like that, which is surely we will not discuss here because that will be a long discussion and we need a dedicated one by one of discussion about that or those schemes. Maybe that's all for this video. I hope you like it, and please comment if you have any question about this video, or maybe you have any request for the next part or maybe other series. Just please let me know. If you like this video, please like and subscribe so I will consistently make my video. Okay, thank you for watching.